Okay, do you see it full screen? All
yes,
good?
Perfect. Yeah, all good.
Okay, good evening, everyone, or good afternoon, wherever you are in the world. So I'm Michele Merelli, and today I am here to present about Particleworks. That is a meshless CFD tool that is used in a wide automotive, not only automotive, but mainly automotive sector. The purpose of the meeting today is to introduce the methodology and actually, okay, this is the training, but I will basically go through the agenda of what we do as a training in Particleworks, focusing today especially in the first part of the training, that is the introduction of the methodology and introduction also of the theory of this of the method that is behind Particleworks. And then I will also discuss about the applications and a little bit of give you an example of a simulation workflow. And I think that more or less there we will stop because we won't have much more time. So just again, to introduce a little bit myself, I'm Michele Merelli. I work in EngineSoft, that is a company that does computational aided engineering in Italy, but also actually in the entire Europe, because this software is sold by us in Europe across every country. Okay, so I do. My main job is to do engineering with simulation and provide to industrial players information about their design and to simulate their design, and we will see in what sector more specifically when we talk about the application. Okay, so feel free to ask me anything also in live, and Jousef, if you can just bounce me the question, I'm happy to answer that. Okay,
Sure, sounds good.
so what is Particleworks? Particleworks, as I mentioned, is a CFD tool, so a computational fluid dynamics tool based on the meshless moving particle simulation approach. Okay, so this approach doesn't require, and we will see in a few slides more in detail, it doesn't require the generation of the computational mesh that you have in conventional CFD. So you can take the CAD as it is, okay? So from the designer, you take, for instance, the transmission of, or the engine, or the piston, or the e-motor, and you directly transfer the geometry to your simulation interface. Here is an overview of the sectors where Particleworks is used, and we will understand why it's used in this sector. The automotive is historically the most important sector, with gear, lubrication, oil, tank, sloshing, car splashing, car wading, but also we have civil engineering with the tsunami scenario, or concrete flow, concrete modeling, but also food and consumer goods. So we can model different fluids, Newtonian and non-Newtonian. So in the food and consumer goods, of course, we have a lot of detergents or very viscous flows and materials. We have chemical engineering with mixing, stirring of high viscosity agents, mold cooling, so also metal casting. So a wider range of applications, really. We will see also some videos for all of them. But let's say, 70% of our customers are in the automotive sector or something like that. And here is a little bit of more detail of the applications. We have a transmission. Historically, gearbox simulation was one of the main fields of application because the software is meshless. So in transmission, we have a lot of splashing phenomena. We have a lot of rotating elements. Okay, you have gears meshing into each other, and the methodology is perfect to analyze this kind of system. We have bearings lubrication with grease. Again, a lot of rotating elements, complex geometries, and that's where the software is has the most advantages. Then you have a motor cooling, engine cooling, piston cooling, but also hydro turbines, water management for rain, soiling, mud simulation. So we have a car maybe entering some sort of wade or some sort of muddy terrain, and viscous flows, so chocolate glue and so on. Okay, so here is just some images. We have also videos coming, so spray cooling, so jets. Whenever we have some jets is also a field of application. Here we have a stirrer. We have some splashing phenomena, mixing. And here I want to give you an overview of the different features of the software. We will go through each one of them, so don't worry about this infinite list. So let's see. As I mentioned, the first feature is for sure the fact that we don't have the mesh generation. We don't have to generate a mesh. So conventional CFD has this sort of Eulerian formulation with a fixed mesh that we have to pre-calculate before running the simulation. And the moving particle simulation proposed by the Professor Koshizuka, this professor at the University of Tokyo, actually so proposed this method and also co-founded Promethex Software, that is the software house behind Particleworks. So you can see an example of from university, from academia to industry, actually. Okay, and the MPS, we see it here, basically discretize the fluid at the beginning of the simulation in particles, and following a Lagrangian formulation, we analyze the fluid flow and we solve the Navier-Stokes equations. Okay. Here is another example of the differences. Instead of creating the, let's say, mesh everywhere in the possible fluid domain, we see here that the fluid and the computational nodes are discretized only where the fluid is at every time step. And then we follow along the flow, and we can have very precise, let's say, discretization and atomization of the flow where needed. So where, of course, the droplets will form. Droplets that are an accumulation of particles, for instance, here. Okay. Here is a little bit of an example of the type of flow that we might want to analyze. As you can see here, we have large deformation of the free surface. This type of phenomena are very difficult to capture with a conventional method, because a priori we don't know about where the flow will go basically, okay? So it's very difficult to prepare a mesh that is correctly discretizing in the region where we need the splashing phenomena. So a priori, it's difficult to know where the splashing phenomena will occur and what resolution we will need there. Okay, so the meshless approach is very suitable for free surface flow, where the surface again has large deformations. Also, the methodology is very suitable when we have translations or rotations, for instance, that we need to apply to the boundary conditions, as we have some examples here. So it's easy to set up moving boundary simulation and boundary conditions, like we have an example here, okay? And again, traditionally, if you have a moving element or a rotating element and you have a mesh, it will be very troublesome to have the dynamic mesh that is able to follow along. So yeah. Regarding the boundary conditions, of course, we have inflow, outflow, pump, and flow resistance type of boundary conditions. As traditional rate and inflow flow rate, very standard boundary conditions. And I want to is this is this going? Got stuck. Okay, there are some videos that are a little bit laggy. Sorry. So in other features, we can do a coupling between the fluid and the structure, actually, and solids. So as you can see here, we have a 6 degree of freedom solids discretized inside Particleworks. So basically, the screws there are discretized as particles interacting with the fluid. And this is an additional feature that the software provides. So like in this way, you can model a floating boat on the sea. That could be another type of simulation that you can perform. So again, you have exchange of forces between the solid component and the fluid. And also another feature is that you can have granular material inside Particleworks. So powders interacted with the fluid or bubbles of air interacted with the fluid. All of these are physics that you can analyze. You can launch Particleworks simulation on graphic interface, graphic GPU. So the graphic cards that you have that you might have on your PC. So you can do CUDA run, and the speed up is quite significant. As you can see here, you can have simulations that are 20 times faster than 4 CPU cores when you move to good GPUs, because the algorithm behind the Particleworks are very parallelizable, okay? The MPS methodology is very parallelizable. So we can simulate we can simulate in a fast way with the graphic cards. It's quite convenient. We have couplings. One coupling, for instance, is with this multi-body simulator that is called the Recurdyne. Recurdyne does the multi-bodies. So for instance, in this application, we have a chain that is modeled with the full 6 degrees of freedom in interaction with the gears. And then we have the co-simulation with Particleworks and Recordine. So basically the fluid is influenced by the position of the solid and vice versa. The solid is it feels the forces and the hindering effect of the fluid. So we have this kind of multi-body dynamics coupling that could be very interesting in some cases. Here is, I just want to give you an overview of the applications and the case studies that we have. We can do chocolate modeling, we can do grease modeling or mud, because again, as I mentioned, we have different non-Newtonian fluid laws, like Bingham plastic, power laws, and so on, okay? And other features, as I mentioned, we can analyze also the bubbling forming inside the fluid due to some sort of interaction between the rotating elements or between the walls and the fluid. So we can analyze air trapped inside the fluid phase, and we can also have evolution of air bubbles inside the fluid phase. Okay. We do have a lot of thermal capabilities. That is also very interesting. Again, I don't want to go in detail, but we have at least 3 ways of analyzing thermal aspects in Particleworks. We can focus on convective heat transfer coefficient estimation. So we can use Nusselt correlations to estimate the heat transfer coefficient on a surface due to the fluid phase. We can analyze the temperature variation inside the fluid, as you can see here, and also the temperature variation inside the solid. Okay, so have a fully coupled simulation between the fluid and the structure. And everything here is done in one interface, automatically meshed by the software. So this is really something new and innovative, because you have a lot of coupling going on, and you have a very fast preparation of your simulation, and very user-friendly simulation workflow. As you can see here, you have convective forces, you have the coffee, in this case, that cools down at the surface with a cup, and you have this kind of also recirculation. Another module inside Particleworks is to account for air. Okay, again, this is an automatically generated mesh that is computed in live during the simulation for air effect. So here is a piston moving the air around a oil jet, and you can see that we have a coupling between the oil injected at the spraying region, and the air moved by the piston. Okay, and again, this is done automatically and without any computational effort. So it's quite innovative, I would say.
Just real quick on the previous diagram, just for the layman, you know, because I'm not, it's completely foreign to me, this area. But what is this telling us about the just as a problem statement? What is this telling us? The animation telling us about this particular product and its performance? Is it working well? Is it not working well? Just out of curiosity, how is this interpreted? Again, the red versus
Yeah, I know. So this is a piston cooling type of application. So what we wouldn't want to look at is actually oil entering the, let's say, impinging on the piston and cooling it. Okay. So the piston would be here, and you have a water jet here that is not reaching actually right now the piston. So ultimately here we want to map the HTC on the piston and see what are the cooled region. And actually we would like to transfer the HTC map to a solver for the thermal aspects of the piston and understand what are the max temperatures, okay? This is just the beginning of the simulation. What we see here is the velocity field. So red means that we have velocity higher than 100 meters per second, okay, in this scale. So it's just a velocity field of air. Red doesn't mean good or bad in this case.
Great, thank you. Very helpful. Yeah.
Okay. So yeah, sorry, I'm going very fast here in a lot of the application and the test cases. But so let's say the software is used to understand mainly if oil reaches and lubricates some areas. Okay, so you want to see the flow and maybe evaluate the wetted areas in a casing, for instance, of a gearbox. It's used for heat transfer coefficient maps on specific areas. So to understand if the surface is cooled correctly or not. It is used to optimize maybe the flow rate inside some channels or like, let's say, I have a gearbox with different compartments. I want to understand if there is some accumulation of oil in one area of the gearbox as compared to the others. But yeah, those are the type of information that we might want to look at. Here we have an example of external field. So this is an aerodynamic field. And actually, we have some contaminant. It could be a droplet of rain that impinges on the surface of the car, and we would like maybe to understand if this will result in some accumulation of water in an area that maybe we don't want, because maybe the contaminant ends up on the mirror, and that will cause some problem, of course, visibility problem. So we can also automate every aspect of the simulation with Python. There is a Python interface that can control the pre-processing, the preparation, the simulation, execution of Particleworks. Okay, it's very nice because the API is quite tailor-made. It's tailor-made on Particleworks, so you can really control every object that you see in the software with the API. So the module, the Particleworks module developed. Okay. And then, okay, there are other aspects of the simulation, other couplings. I don't want to go in detail because those are very advanced topics, but we have integration with ANSYS Workbench, integration with other simulation tools like Romax, and so on. Okay. Do you have maybe some question or on this part? Or curiosity?
Only, I mean, I paid a little bit of attention yesterday was a little bit harder for me to appreciate, but this lattice Boltzmann method that was introduced yesterday was also, I guess, quote unquote, a meshless approach, if I'm not mistaken. And not in an attempt to appreciate the lattice Boltzmann method, but just to compare and contrast, so I can, appreciate a little bit. What's the, are they in the same sort of category? They're looking at individual particles and solving these equations versus a full-fledged, I guess, macroscopic model. Are they similar in their approach?
They're similar because they are meshless, but lattice Boltzmann at the end works with a Cartesian grid, I would say, right? I'm not super expert on that. You can have local refinement in that case, right? But the moving particle simulation, it's unique because basically the computational nodes are localized only where the particles are. Okay, while the lattice Boltzmann, it's something more like we see here. So at least to the degree I know about.
But that's good enough. I mean, I'm not so I'm a layman. So for me, the takeaway is yes, they're similar because they're meshless, but there's various differences between the two. Got it.
Yeah.
Good enough for you. Okay.
And one is more focused maybe on the air simulation. The other one is more focused on the also fluid and splashing and jets. Okay. So lattice Boltzmann, for instance, is widely used, I think, in external aerodynamics. Actually, Particleworks has a lattice Boltzmann solver inside for the air simulation. Okay.
We got a clarification from Jousef that it's not meshless, but works with lattices, which is a concept introduced yesterday.
Yeah.
Okay.
Yeah.
But this particle is quote unquote meshless, whereas LBM is lattices. Got it.
Yeah. Okay, I think it's a little bit more theoretical today, so I will briefly touch on the theory, just to give you a little bit of an overview of where Particleworks and MPS is located. So I would say that the closest meshless approach is actually SPH. It's another particle-based meshless approach, in which we deal with compressible fluids. There are other software commercially available based on the SPH. Particleworks is based on MPS, is for incompressible fluids only. And this means that the type of simulation that we can do is a little bit more limited, but actually the stability requirement is a little bit less conservative for MPS. As you can see here, the ratio between the current, particle size, and Umax is actually more. So let's say usually we can work with a simulation that is 10 to 100 times faster in MPS, because again, the incompressibility of the fluid stabilizes a little bit the simulation by itself. So, or at least we have a possibility to restrict the velocity field, meaning that we can work with a DT that is smaller, higher. This is a little bit the difference. You might have heard of SPH, and this is the difference with MPS. In terms of equations, those are the equations, the usual equations that you find in a Eulerian mesh-based CFD tool. It's just that we use the material derivative instead of the Eulerian derivative. So we basically change we rewrite the Eulerian term here with the material derivative term. And those are the equations. And the energy conservation law is activated only when the thermal aspects are enabled. Okay. But this slide tells us that we are dealing with the same equations, basically, of the conventional tools. Okay, a little bit on the theory again. The MPS differs from the SPH in terms of the kernel function that describes the repulsion, sort of repulsions, that particle feels to each other as soon as they approach closer and closer to each other. As you can see here, the repulsion goes to infinity when the distance is smaller than the particle size. So this is the radius of the particle, and when they approach, let's say, half of the radius or more, this goes to very high repulsion forces. SPH can allow for fully superimposed particles because it's compressible. Okay. We have this concept of particle number density that is that needs to stay in a certain range. So we have a maximum amount of particles that can fit in this sphere. Otherwise, again, if too many particles enter this sphere, it means that we are in the comprimibility region. Okay, so yeah, there is this concept again. For now, it's not that important to articulate more in detail, but the number density is basically used to analyze the stability of our solution, because again, it tells us about the comprimibility or not of the fluid. We have
just one question. Yeah. So as we move from one time step to the next using the explicit time marching, so at all the times do we need to keep check on like what is the particle density inside that region, or
yeah, basically yes. I mean, not every time step, but every saved output, because I mean, you have a transit simulation, intrinsically transit simulation here. You don't have residuals. You will save every sort of, I don't know, maybe 1 millisecond. You have a result, okay? For every result, you can monitor some stability aspects like the number density, average number density. You can have a look at the results itself and understand if it's reasonable or not in terms of flow. Most of the cases, you see explosions, you see not physical behaviors, you see particles maybe going through the walls. So all of them are indication of unstable results, okay?
Okay, yeah, thanks.
In terms of discretization of the differentials, the methodology is different here because we are dealing with a discrete type of mesh or let's say computational grid, dynamic computational grid. We don't have a completely filled, let's say, region here, a continuous region, but we have discretized particles. And so in this sense, we have a sum here, not an integral. And we do a weighted average distribution of the properties and diffusion of the properties like pressure, velocity, and so on. Okay, so we rewrite the Laplacian gradient operators with this kind of sum. Okay. Okay, I will skip a little bit, I guess, this. Here is the algorithm. So you starting from an initial position and pressure, you first compute the viscosity and gravity terms, and you update the particle position. And then you can decide for actually two types of pressure solvers. One is the implicit and one is the explicit solver. The Poisson equation is solved for the implicit in case it's this methodology used. Otherwise, we can have an explicit pressure estimation that will be much faster. Actually, this one is twice or 3 times as faster as the implicit one. And then for every time step, you update the position after the pressure is taken into account, and you do iterative, you do an iteration, okay? I will just skip a little bit here and there because I mean, for now, I don't think that we want to go in the details. Every features that we touched previously, like the airflow, air resistance, of course, we'll add some terms in the Navier-Stokes equations. We have 2 solvers for surface tension. So Particleworks is able to also analyze the surface tension of your fluid surface. So the curvature, for instance, of droplets on a surface. And we have also, as I mentioned, different heat transfer and heat conduction capabilities. We have the possibility to define a current limiter or a velocity limiter for improved stability of our simulation. And we have a turbulence model and the non-Newtonian fluid laws, okay, and different numerical models there. Again, I already discussed them, and you can see, of course, that numerical methods follows along the applications that we touch. Maybe it's good to discuss in 5 minutes the simulation process and the graphic user interface, just to give you an idea, as I think that some of you might be new to the interface of Particleworks, even if we introduced a little bit a couple of weeks back. So what you see as compared to the conventional method is that here we don't have the mesh generation step. So we start directly with the condition settings, and this usually means that we cut the simulation process by at least 1/3. We reduce it by 1/3. And the multi-GPU acceleration can also speed up the simulation steps, okay? Also, we don't have the criticality of mesh quality for convergence of the simulation. So usually it's quite stable, our simulation workflow. What you need to do in the workflow is to start from your CAD. You want to export in STL, so surface type of surface geometry, or OBJ, also Nastra formats, and you want to export without without simplification actually of the geometry from the CAD. You just want to export separately, perhaps the casing that doesn't rotate or move, and the gears in this case, as every gear will have a specific rotational speed. We want to separate them in the CAD and in the export. And then you can see that we can compose the the case. Then we would define the various conditions like the particle size, the time step for the simulation, with the physics, so the viscosity and thermal aspects, the material properties, and the, again, numerical settings. Then you would have the pre-processing. In the pre-processing, for instance, here we see that the fluid is initialized below a certain filling level, okay? So during the preparation, we might want to define a filling level, and automatically the software will understand the inner region of the casing and will create the fluid, as you can see here, during the pre-processing. In the pre-processing, the mesh at the interface, so the solid, will be discretized automatically. So basically, starting from the STL, we have a discretization with a Cartesian grid with a specific grid size of the walls. And this is again done automatically, okay? And the fluid is discretized again with the particles. Then we would have the execution, better on GPU, but we can also have CPU execution. And the post-processing. Everything is done in one interface, starting from the definition of the simulation to the post-processing, okay? And in terms of post-processing, we can look at the color map on the fluid. We can have a visualization of the flow, very easy visualization of the flow. Surface rendering, we can look at torque or forces on the rotating elements. We can do streamlines or generate videos, images, a lot of basic post-processing. The graphic user interface, just to guide you, this is how the software looks like. You have on top here the generation of a new project, the numerical settings, and all the post-processing on top here. Here you have a description of your simulation with the input objects, the geometry objects, the gravity, and so on, the inflows, the outflows region, and so on. In the result, you will be able to see what you generate during the simulation, like the particles of the fluid. And at the bottom here, whenever you select an element, you will be able to control the physical properties, the geometrical properties, the keyframes, so the rotations, the positions of that element. So it's very easy actually to check and to change the settings, and it's done in one interface. At the bottom, you have a player to visualize and play the results. And you have also a color map region here to control for the visualization of specific, so to control for the visualization of the output, like here we have the velocity plotted on the particles.
Just a quick question on the tool again, just again from a layman perspective. How is the simulation of the rotation of these gears and how they interact with one another? What I was following earlier was the simulation is performed on the particles that are around the gears. Is the tool also simulating how the gears interact with one another?
Sure. So here we don't have a play button, but we would see this rotating, the fluid lifted up. So the position it's controlled by us. So we are not modeling the solid-to-solid interaction, nor we are understanding, for instance, the friction there. Okay, that is imposed by the user. But yeah, other than that, the fluid is lifted by the gears and the interaction of the gears. Does it answer the question?
Yeah, yeah, but there is the relationship between the gears, the physical object, and the fluids is modeled, but not the gear.
Yeah.
Okay.
We define for every object the rotational center, the RPM that comes from, yeah.
Got it, thanks.
Here is a little bit of a post-processing example. So as soon as we launch a post-processing, we will see it appear on the right. Okay. I don't want to go farther, I think. Do you have questions? I went a little bit fast, I know. So perhaps it's a good time to
I have a question. You mentioned something about particle size. How do you define that?
Yeah, usually the smaller the better. But the best practice is if you have like a channel and you want to understand what is the flow in that channel, you have to at least have 3 to 5 particles inside the channel flow. Okay, so if you have 1 millimeter region of the channel, so the channel is 1 millimeter in width, you at least have to define a particle size of 0.3 millimeter or smaller. You much sooner get a computational limit than other more sophisticated consideration, actually, in terms of how small you can get, because as you halve the particle size, you will look at approximately 10 times slower particle simulation because of the scaling of the number of particles you generate. Okay, so if you think about the scaling of the volumes, as soon as you halve the particle dimension, you can expect that the number of particles you generate grows quite significantly. It's not a factor of 2, but a factor of 8, 2 to the third power. Okay, so in most of the cases, you try to go small enough to resolve for the gaps you have in the geometry, but in most cases you hit some computational limits faster than I mean, usually that is the limit. Okay, it's a computational limit, not a particle size limit. Okay. Does it answer the question?
Yeah, thank you.
Other questions? Curiosities?
I think
is it possible to
Go ahead, sorry.
Yes, sir. Thanks. So is it possible to model viscoelastic fluids in this case? And
yes,
that is the first question. And one more question I have is like, as you said about parallelization. So even though this lattice Boltzmann method is highly parallelizable, so is there any benchmark study that is available? Like what is the core count to which it has been validated for some test cases?
Okay, so we do have the possibility of analyzing viscoelastic flows because we can define power laws, we can define any sort of function actually describing the rheology of your system, also temperature dependent viscosity and so on. Okay. The second question was about sorry, the validation.
I mean, like to what course it has been, like the weak and strong scaling. I mean, like if there is a study on like how the solver scales for a given problem size, but increasing the CPU count, and like
Okay.
in terms of solving a larger size problem, increasing
Yeah.
the CPUs.
Yeah, so we do have CPU scaling, but also GPU scaling, multi-GPU scaling. Let's say, as usually we work with models in the range of 10 to 100 million particles, and usually a good GPU can be compared to 60 cores. Okay, that is a little bit, but it can vary strongly on the physics you apply, the number of particles you have. Then the multi-GPU capabilities will scale again, sort of linearly. So the simulation time will decrease by a factor of 2 as soon as you have 2 GPUs, okay? Here you have an example of the scaling with cores and the GPU, but yeah, publicly available scaling, that's all we have.
All right.
And we don't have comparison with other approaches, unfortunately. Okay. Not that I know.
Cool. I would have one question, Michelle. Yeah. More of an organizational one, which is I was asking people earlier on if they have availability of to the license, which is not the case. Do you have any estimate on when the license will be activated?
Yeah. So we need to, I don't know, maybe discuss it also a little bit later on. But so you sent correctly the MAC addresses and the informations. That's very good. We shared them with the developers of the software that are actually willing to give the software if we have an official request from actually academic users with the academic emails. That's their policy right now because of confidentiality and also actually some sort of yeah, let's say policy, internal policy they have. So we need to have at least some, unfortunately this is the situation for licensing, we need to have some university affiliation and formal request with university email addresses. That is the situation. If we are dealing with companies, also here the Promethex software does a little bit of a selection, let's say, of type of company that is willing to collaborate with, or at least that is interested to collaborate with, that are a little bit on the engineering or the manufacturing side. So this is the policy for licensing, for the trial licensing, again, to also safeguard some confidentiality aspects of the methodology. Because as soon as you have the software, you have also access to the documentation. So yeah, this is the situation. I hope it's not a big problem.
Okay, someone else asks in the chat, he graduated a year ago, but still has access to his NTU email and academic login. Does that work? What do you think?
Yes, if you have an email that you can send, an academic email, yes. that. So we will send the license to the academic email, basically.
Mm-hmm.
Okay. So you still have to have access. Yeah.
Great.
Sorry about that. Sorry about that, but.
Cool. All right. Any more questions, guys? I would have maybe one, Michelle. I'm not sure if you mentioned it during your talk, but what are the limitations of the particle-based approach? For example, would we be able to solve hypersonic flow, anything like that, or is that something where you say no?
So we are in the incompressible fluids, so range. We don't have Mach greater than 0.2.
Okay.
We don't have phase exchanges, phase change. So we don't have evaporation. We don't have solidification. The advantages are a little bit smaller as soon as you have closed the system, like maybe pipes. In there, you don't have so flowing pipes. You don't have a free surface flow, right? So in that case, the advantages of the meshless approach are a little bit smaller. But the advantages is that you don't have to generate the mesh. So if you have also for internal flow some very complex geometries like batteries simulation, if you want to do some battery cooling simulation, even if it's all internal flow, for instance, you might struggle quite a bit because of the complexity of the geometry.
Interesting.
Other limitations, I don't know. Like it's intrinsically transient, so sometimes to achieve the steady state solution, it might take quite a bit of time. That's all I have.
Good. Okay. Excellent. All right. Any more questions from the audience? Otherwise, we'll wrap it up.
I have one question. Is this software capable of simulating 6 degrees of freedom, like more in, not like rotating, but like in translation, for example, like objects falling into a liquid?
Yeah. As I showed you in this slide a little bit fast, in a fast way, we do have two types of boundary condition for solid. One is a boundary condition that we control ourselves, for instance, the rotation of the position, like the external wall and also the fan. But then you see that you have solids floating and moved around by the fluid. Those are discretized with particles inside the software, and they have 6 degrees of freedom. Okay.
Okay, great. Thanks.
And then you have also the capability of coupling with a multibody that has 6 degrees of freedom, but let's say handled outside the software. Okay.
Yeah.
Great questions. Cool. Otherwise, thank you so much, Michel, for the presentation.
Okay.
Really enjoyed it. Is there a possibility to get the slides from you?
Those slides, I might want to select some. Okay. In PDF form, I should be able to give it to you also, maybe in PPT form. Yes, I will try to send it to you. Yeah.
Perfect. Awesome, Michel. Thank you so much.
I just want to ask you if you want to also maybe follow along on LinkedIn. We are on LinkedIn with the page Particleworks Europe. So it will be nice if you go there and check our content, because you can be updated on the capabilities and in general our events. So yeah, please check it out. Particleworks Europe.
I posted it in the chat, so we have 9 more followers until you hit 1,000. So
yes, let's eat that.
Guys and girls, make sure to hit 1K for Particleworks. Cool.
Amazing. So thank you for
your
thank you for your time, everyone, and for your interest. Let's keep the discussion on the licensing open in the coming days, and see what we can do about that.
Perfect. Thank you so much. I'll see you guys in 15 minutes on generative engineering then. Thanks, Michel.
Enjoy the rest of the day. Bye. Bye.
Bye-bye.